I wanted to just start by showing you one thing to follow up on the class from last week. Right, so last week we were talking about the operators for spin, so the Sx, Sy, and Sz, and how to express those things as matrices when we're dealing with particles of spin a half, right? And so we got to these equations, right, for each of those operators expressed as a matrix, okay? And then we talked about the eigenvalues and eigenvectors for S sub z, right? That these are those two states. So the eigenvectors are 1, 0, and 0, 1, right? And these things correspond to the states that could be labeled as the up ket and the down ket, right? And then for Sx, I showed you that the eigenvalues are the same, plus a half h bar and minus a half h bar. And the corresponding eigenvectors are these two vectors, right? And the first eigenvector goes with the first eigenvalue, and the second eigenvector goes with the second eigenvalue. I think I couldn't find in my notes about the eigenvalues and eigenvectors of Sy, so here are the results to show you. Okay, so the eigenvalue of plus a half h bar goes with this eigenvector, and the eigenvalue of minus a half h bar goes with this eigenvector, as you can check by just multiplying it out, right? To multiply this matrix times this vector or this vector. So for me, when I look at a table like this, it just seems so weird to think that a state that has spin in, say, the plus x direction, so that would be this state, you know, to think that that is a linear combination of the up state and the down state with certain relative phases, right? And then the state that's aligned with its spin in the y direction is also a linear combination of the up state and the down state with different relative phases. There isn't really any classical analog of that statement. That's a quantum mechanical phenomenon. And I don't have a really intuitive picture of that, but it does follow from the general mathematical considerations that we've been developing through the semester. And so, so I don't have any great intuition to pass on to you, but you know, these are mathematical results that you can use for solving problems, right? So when you see in a problem that, say, a particle has its spin in the plus y direction, that means the particle is in this state, right? And if you see a problem that asks a question, like, what's the probability that if you observe the spin in the plus, that you will see a spin in the plus y direction, okay? That means that you take the inner product between the state and this thing, and that inner product, magnitude squared, gives you the probability. So this is a state that you can use in the same way that we've been using states all through the semester, right? To figure out the probabilities and expectation values. So there will be a homework where you have to do things like this. I think I'll post it tomorrow. The homework with working with spin vectors. Okay, so, what I mean to do for the rest of today is to talk about um, uh, an example of um, how to work with um, spins to, model a certain kind of experiment. Okay, so are there questions about the sort of general theory before I go on to an example, or maybe the example will help to clarify what's going on? Okay, good, good, good. Okay, let's do that. Okay, so we're going to talk about spin and magnetism. So to talk about that, let me first remind you of something from classical E&M, which hopefully you've seen in university physics or in E&M class. Okay, and that is that if suppose you have a spinning object like a baseball. So here is a baseball and it's spinning, okay, about an axis like this. Okay, so this object has angular momentum. And so we could describe that by some angular momentum vector, a spin vector, which is like this, right? And so that means that, if you use the right-hand rule, right? If your thumb is along that vector, then your fingers show which way the object is spinning. Okay. Now, if the object has electrical charges, okay, so suppose there's a whole bunch of charges all through the object. Okay. If the object has electrical charges, then it also has a magnetic dipole moment. Right? And the magnetic dipole moment is also aligned in this spin direction along this axis. I'll call it a magnetic dipole moment mu. Okay? And the reason why there's a magnetic dipole moment is just that when the object is spinning, there are all these electrical charges that are moving. Right? And you know that when electrical charges move, they generate magnetic dipole moment. So if they move in a circle about the axis, then they generate a magnetic dipole moment along the axis, right? And up or down along the axis, depending on whether they're positive or negative charges. Okay, so the spinning creates both of those things, angular momentum and a molecular dipole moment. Okay? And those two things are related to each other. Right? And so we could say that the magnetic dipole moment mu is equal to a constant times the spin angular momentum s. And this constant gamma is called the gyromagnetic ratio. That word is a compound word, right? And so gyro is like gyroscope, refers to spinning, and then magnetic is the second half of the word. And as usual with these compound words, the first half represents the cause, and the second half represents the effect, right? And so the spinning is the cause, and the magnetic dipole moment is the effect. Okay, so now what determines that gyromagnetic ratio? Right? Well, it depends on the relative distributions of the charges and the mass. Distribution of, let's say mass and charge. So if the mass is all near the center and the charge is out near the edge of the ball, okay, then the spinning mass makes a relatively small angular momentum, but the spinning charge that's farther out makes a big magnetic moment. And so then the gyromagnetic ratio is big, okay? And if it's the other way around, if the mass is out near the surface and the charge is mostly in the center, okay, then the spinning mass makes a big angular momentum, but the spinning charge just makes a little magnetic dipole moment. So the gyromagnetic ratio is small. Okay. Now, if the distributions are the same, so for example, if the mass and charge are both uniformly distributed throughout the ball, okay, then there's some classical result for the gyromagnetic ratio. That the classical gamma is equal to the charge divided by 2m. Now, let's apply all these considerations to an electron in quantum mechanics. For an electron, okay, it also has spin, angular momentum. It also has a magnetic dipole moment. So there will be some ratio between those two things, a gyromagnetic ratio. So you might think, based on these classical considerations, that should depend on the distribution of the mass and the distribution of the charge inside the electron. But what does that even mean? The distribution of mass inside an electron or the distribution of charge? I have no idea of what those distributions are. I don't even know if that's a physically meaningful question to ask. Right? So if I had to guess, my guess might be, I don't know, maybe they're the same, whatever these things are. Okay, so maybe I would guess that the gyromagnetic ratio would be the charge, which is negative E, divided by 2 times the mass of the electron. Okay, so that's my guess. Actually, that guess is wrong. It's not bad, but it's wrong. Okay, so actually, these things are really related by a factor called G, okay? E over 2, mass of the electron. Okay, and this thing called G, people truly refer to this in quantum mechanics as the G factor. I don't know why they call it the G factor, but they call it the G factor, okay? And it is approximately 2, okay? And so my guess was off by a factor of 2, approximately. Okay, now, I have to tell you, weirdly, this G factor for the electron, this is about the most precisely known number in all of physics. It is measured experimentally to incredible precision. So there are precise experiments, and they give G is 2.00. Okay, I'm copying this from my notes. I hope I got this right. 23192.304.386. These are all really significant figures. Right? People have actually measured all of this. Okay, and this has also been calculated through a more advanced version of quantum mechanics called quantum electrodynamics, which is abbreviated QED. Okay, and that's something which you may learn in a more advanced course, but you're not going to learn from me. Anyway, it's calculated to all these significant figures. It actually agrees with the experiment. This is like an amazing triumph of theoretical and experimental physics to measure and calculate anything to this many digits and see an agreement. But this is actually true. Okay, so this is just the remarkable bit of trivia for the day. Okay, so anyway, the point is that an electron is spinning, and so it has spin angular momentum, and it also has a magnetic dipole moment. Okay, so let's go back to that. Okay, so we'll go back to saying that there is an electron magnetic dipole moment. Okay, which is this mu is the gyromagnetic ratio times S. Okay, that means that if you put the electron in a magnetic field, then there's some energy of the magnetic dipole moment in a magnetic field. So we'll say, what is the energy of a magnetic dipole in a magnetic field? Okay, and so that gives you a Hamiltonian, which is negative mu dot B. Okay, so mu is the magnetic dipole moment and B is the applied magnetic field. Okay, is that kind of familiar from E&M classes or university physics? Okay, good. Now, if we combine that equation with the equation for what's the magnetic dipole moment, okay, we get an energy that depends on the spin. So this is negative gamma B dot S, okay, where S is the spin operator. So this is the simplest example where the spin operator goes into the Hamiltonian. Okay, so that is the energy depends on the spin state. So let me show you an example of how we could work with this. So suppose that we apply a magnetic field in the Z direction. So B is in the Z direction. So the B vector is some B naught times the unit vector in the Z direction. Okay, then the Hamiltonian is negative gamma B naught times S sub Z. Okay, so it's, BX times SX plus BY times SY plus BZ times SZ. But Bx and By are 0. So it's just Bz, which is this thing. Okay, so that means that the Hamiltonian depends on the spin state, and we could write it as negative gamma B naught times h bar over 2 times this matrix 1, 0, 0, minus 1. So this then is the Hamiltonian as an operator acting on spin states. Okay, so then what? Then we can say that the eigenstates of the Hamiltonian are the same thing as the eigenstates of SZ, right? Because this is just a scalar, there's a scalar times SZ. And we know what the eigenstates of SZ are. That's what I showed you in the first slide in this class. Okay, so those eigenstates are the states 1, 0, and 0, 1. Or equivalently, we could write them as up and down. Okay, so that means now we know the eigenstates of the Hamiltonian. Okay. The eigenstates of the Hamiltonian are 1, 0, and 0, 1, and each of them has some energy. This state has an energy E up, which is equal to negative gamma B naught h bar over 2. And this one has energy E down is plus gamma B naught h bar over 2. Is that clear? Just to make sure? Let me just make sure. I'm not positive everyone could follow that one. Okay, if we have the Hamiltonian, acting on 1, 0, that means negative gamma B naught h bar over 2, 1, 0, 0, minus 1, acting on 1, 0. And that is negative gamma B naught. Yikes, what am I doing here? B naught h bar over 2, much better. Okay, negative gamma B naught h bar over 2. And then if I multiply out the matrix times the vector, okay, that is on the top 1 times 1 plus 0 times 0. On the bottom, 1 times 0 plus 0 times minus 1. Okay, and that is equal to E up times the state 1, 0. Okay, so E up equals this thing. Okay, and likewise, H acting on 0, 1 through the same argument, it's equal to positive gamma B naught h bar over 2 times 0, 1, which is E down times 0, 1. Okay, so now we know the two eigenstates of the Hamiltonian. That means we know these things are the solution of the time-independent Schrödinger equation. Okay. So we can then solve the time-dependent Schrödinger equation. All right. So the time-dependent Schrödinger equation is that IH bar d by dt of our state chi, that's what the textbook is using for a magnetic state, is equal to the Hamiltonian acting on chi. Okay. And the solution is that the general chi as a function of time is the sum over the eigenstates of the Hamiltonian of some coefficient c sub I times chi I times e to the minus I energy t over h bar. Maybe I should use the subscript n instead of I, to be clear. E chi n, okay, nt over h bar. Okay, now n has two possibilities, just two, count them, up or down. Okay, so n equals up or down. Okay, so this thing is C up, then the up state is 1, 0, e to the minus I e up t over h bar. Then plus C down, the down state is 0, 1, e to the minus I e down t over h bar. Okay, so this is a time-dependent solution which has two arbitrary coefficients in it, here and there. So these are coefficients which are determined by the initial conditions, as they always are in this semester. Okay, so then, we have to make up some initial condition. Okay, so let's suppose the initial condition is chi at time 0 is just AB. Okay, and this, it must be normalized, right? We have to be assuming a normalized initial condition. Whoops. Okay, so when we say that it's normalized, that means the inner product of chi with chi equals 1. Okay. That means that the row vector A star B star times the column vector AB is 1. Or if we multiply this out, that absolute value of A squared plus the absolute value of B squared is 1. Okay? All right. So if we have that initial condition, that should be enough to determine what are C up and C down. Okay. So in here's our equation for chi at any time t. If we plug in t equals 0, we get chi at time t equals 0. That's C up 1 times 1, 0. Okay, and the exponential of 0 is 1, plus C down times 0, 1, and the exponential of 0 is 1. And this is equal to C up, C down. Okay, so we have that this has to match AB, right? This equals C up, C down. Okay, so therefore, C up is A and C down is B. Okay, so with that, we get our solution. Okay, so our solution is that at any time, chi of t is A times 1, 0 times the exponential e to the minus I e up t over h bar plus b times 0, 1 e to the minus I e down t over h bar. Or I could write this more compactly by combining all these things. So this is just a vector where on the top we have A e to the minus I e up t over h bar. And on the bottom, we have e to the minus I e down t over h bar. Or we can actually use what we know are E up and E down. Right? We have these expressions over here for E up and E down. Okay? So if I put those things in, then this solution is A e to the I gamma b naught t over 2, and b e to the negative I gamma b naught t over 2. Okay, so this is the solution of Schrodinger's equation for this spin problem. Okay? And so this solution is a spinor, a vector, right? And so this solution is telling us that the spinor is changing in time, right? That the spinor has these components there and there, which match the initial condition at time t equals 0, and then they're gradually evolving in time. So this is like the solutions to Schrödinger's equation that we've done earlier in the semester, right? Earlier in the semester, we had a wave function that depends on position and time, okay? Here, we have something that depends on the spin coordinate and time, right? So it's not a function of x and t, but it's a function of spin and t, right? Those two spin states are up and down. Okay? There are two possible spin states, right? So it's like my joke example where the particle had two possible positions. But here it's realistic. Electrons really do have two spin states. Okay? And I'm neglecting position. I'm considering that position is not an important variable here. So I'm just not thinking about position here. But I'll talk about position a little bit more at the end of the class. Okay, so this now is a wave function, okay? And it's a normalized wave function. So that is, it starts normalized at time t equals 0, and it stays normalized as we evolve, right? And so I set things up so that it was normalized at t equals 0, but then it stays normalized as a function of time, okay? Now, what can we do with this solution, right? Well, we can use it the same way we've used wave functions all through the semester, which is to calculate expectation values, all right? So all through the semester, we've calculated expectation values of position and momentum, right? Or position squared, momentum squared, okay? Now, we have spin. So let's calculate the expectation value of spin, okay? So in this state, we could calculate the expectation value of SZ or SX or SY, any of those things. So let's do it, okay? So suppose we want to know what is the expectation value of SZ in that state that we just found. So that is, what is the inner product of chi, the bra chi, acting on SZ, acting on the ket chi, like that. We can multiply this out. Okay, so let's do it from right to left, okay? So the ket chi is A e to the I gamma B naught T over 2. B e to the minus I gamma B naught T over 2. Okay, that's the ket. Then we need the operator, okay? The SZ operator is H bar over 2, 1, 0, 0, minus 1. Okay. Then we need the chi bra. So that's a row vector, which is the complex conjugate of everything that goes in the ket. Okay. So this is A star e to the minus I gamma B naught T over 2, and then B star e to the I gamma B naught T over 2. All right, now let's do the matrix multiplication. Okay, so here, again, I'll work from right to left. Okay, so if I'm multiplying this 2 by 2 matrix times this column vector, okay, so that gives us still h bar over 2, and we have a column vector. On the top of the column vector is a e to the I gamma b naught t over 2. So 1 times this plus 0 times the thing on the bottom. On the bottom of this column vector, I have 0 times the a thing plus -1 times the b thing. So negative b e to the minus I gamma b naught t over 2. And all of that times this same row vector. Okay, now let's multiply that out. Okay, so the factor of h bar over 2 just comes out. Okay, and so we have the first thing times the first. Okay, so that gives us a star times e to the minus stuff times a times e to the plus stuff. Okay, so it's just that. Okay, and then minus b star b. And again, the complex exponentials cancel. And this is just h bar over 2, a magnitude squared minus b magnitude squared. You'll notice that this is independent of time. And that is reasonable. It should be independent of time because the operator SZ commutes with the Hamiltonian, right? And the way that an expectation value changes in time depends on the commutator of that operator with the Hamiltonian, right? We proved that in general. Here is a specific example of that being true. Okay, so that works with SZ. Now let's do it with the other components of spin. Okay, so actually I want to just, can I copy and paste this page and then just change the calculation? I bet I can. Let me see how I do that. Can I say here, duplicate? Cool. All right. So now if I duplicate this, here, I'll do the thing that students hate where I just erase something and then change it. Okay, so if I change the SZ to an SX, okay, so what if I want to know this expectation value as a function of time? Okay, so this is SX. So it's the same state chi, but it's a different operator. The operator here is h bar over 2 times 0, 1, 1, 0. A different matrix goes here. Okay, so now I need to do the matrix multiplication. All right, so once again, I'll work from right to left. Okay, So in this matrix multiplication, I have on the top 0 times the A thing plus 1 times the B thing. Okay? So that makes B e to the minus I gamma B naught T over 2. On the bottom, I have 1 times the A thing plus 0 times the B thing. So A e to the I gamma B naught T over 2. Okay. Now I will multiply out the row vector times the column vector. Okay. So we have the top times the top. Okay. So that gives us A star B e to the minus I gamma B naught T, not over 2, because there's 2 factors of that thing. Okay. And then the second times the second. Okay. So that's plus B star A e to the I gamma B naught T. Okay. Yes. So this is SX, expectation value. And this is not independent of time, right? It depends on time. It is changing in time because the commutator of the Hamiltonian with Sx is not equal to 0. We know it is not equal to 0 because the Hamiltonian is proportional to Sz, and Sz does not commute with Sx. Okay, how about for Sy? Okay, well, I'll do my copying thing again. Okay, duplicate. Great. All right, how about for Sx? I'll do that one in, or Sy, excuse me, I'll do that in blue. Okay, so Sy, that is this expectation value here. Okay, so the inner product, chi acting on Sy acting on chi. Okay. Once again, the only thing that we need to change is the 2x2 matrix that goes here. Okay. So this is 0 minus I 0. Okay, now what? Now, again, I'll multiply these things out right to left. On the top, I have negative I times the B e to the minus I gamma B naught T over 2. And on the bottom, I have IA e to the I gamma B naught T over 2. Okay, and now I can multiply out the row vector times the column vector. And so that gives us negative I A star B e to the minus I gamma B naught T over 2. And then plus I B star A e to the I gamma B naught T. Whoops, no, not over 2. Not over 2. Oops. Sorry about that. Okay. All right, that matches my notes. Good, good, good. And once again, it depends on time. Okay, so now we have these three results. Okay, so for the three components of the spin expectation values. Okay, so well, what do they mean? Okay, so if we want to interpret this stuff, okay, first of all, remember the normalization. Okay. We have the normalization that the magnitude of a squared plus the magnitude of b squared is equal to 1. Okay, so there's one clever way to make an assumption that enforces this constraint, okay? So you know that with any angle, right, the cosine squared plus the sine squared equals 1, right? So if we wanted to be clever, we could say, ooh, let's make A to be the cosine of an angle and B to be the sine of an angle. Okay, that would be pretty clever. But the guys who wrote the textbook are even more clever. And so to be even more clever, they say, let's let A be the cosine of alpha over 2. And B is the sine of alpha over 2. And you're thinking, alpha over 2? Why alpha over 2? Well, you'll see in a minute why alpha over 2. Okay, so suppose you go with this, okay? And so suppose you put in these assumptions for A and B. Okay, and now let's put these assumptions into the expectation values that we figured out. Okay, so the SZ expectation value is then what? It is h bar over 2, and we said magnitude of a squared minus magnitude of b squared. Okay, so that is h bar over 2 times the cosine squared of alpha over 2 minus the sine squared of alpha over 2. And now, if you remember your trig identities, you can recognize that the cosine squared minus the sine squared is equal to the cosine of the double angle, right? And so this is the cosine of double alpha over 2, which is just alpha. So h bar over 2 cosine alpha, okay? That's why they said the even more clever alpha over 2, okay? So make it easier here. Okay, now what about Sx and Sy? So for Sx average, okay, that is h bar over 2 a star b to the minus I gamma b naught t plus b star a e to the I gamma b naught t. Okay, so this is h bar over 2, and a star b and b star a, right? Those things are both equal to cosine alpha over 2 sine alpha over 2. And then we have just this exponential plus this exponential. And this thing is 2 cosine gamma b naught t. And this thing is a sine of a double angle thing. So it's a half sine alpha. Okay. So combining those, we get h bar over 2 sine alpha cosine gamma b naught t. Incidentally, as a nice check, you can see that this is real. It better be real, right? Because it's an observable quantity, right? The expectation value of the spin in some direction. So it's the expectation value of a Hermitian operator. It better be real. Okay, and then likewise, the expectation value of SY, it's all the same kinds of considerations. It is, let's see, h bar over 2 cos alpha over 2 sine alpha over 2. And then there's a negative I e to the minus I gamma b naught t plus I e to the I gamma b naught t. So this all is negative 2 sine gamma b naught t. And this is still a half sine alpha. All right, so this all works out to be negative h bar over 2 sine alpha sine gamma b naught t. Also real. Okay, so now we can see how all 3 components of the spin expectation value are changing in time. Okay, so we can see that the spin expectation value has a fixed z component that is constant with respect to time, and it has x and y components that are varying in time as sine and cosine. Okay, so if we make a 3D drawing of that, the expectation value of the spin, that is a vector like this. Okay, this is the expectation value of the spin. And here is the magnetic field in the z direction. Okay, and so the expectation value of the spin is precessing around a cone like this, right? So if it's like my Apple Pencil, it goes around in a cone with a fixed height. And so the x and y components are changing in time. The z component is not changing, okay? The word for this is Larmor precession. About the magnetic field. Okay, and so this is showing us, right, that the quantum mechanical spin of an electron does the same thing that you would expect for a classical magnetic moment, right? This is a calculation that you may have done in class, right, for a classical magnetic moment. And if it's not perfectly aligned with the field, then it tends to precess around the field. And here we are calculating the frequency of the Larmor precession. So it's this omega Larmor is the thing that multiplies time inside these sine and cosine. And so it's gamma B naught. Like that. Right? So this is indeed a quantum mechanical version of the classical result for precession. Right? So this is something that quantum mechanical spins do. Okay? And so for quantum mechanical spins, we could calculate this precession property. So this is one example of what we could do in a spin problem, right? Of how to calculate what's the spinner as a function of time, and then using that spinner, you could say what is the expectation value of Sx or Sy or Sc. And then one more thing, I wasn't planning to show this, but maybe I should. There could also be in a problem a question like, suppose you measure Sx. What is the probability you would get plus a half h bar? Right. So that probability is, as always, it's the magnitude squared of an inner product. Right? So the probability is the magnitude squared of an inner product between the state chi and the state with Sx equals h bar over 2. Right? And so the state with Sx equals h bar over 2, how do I write that? The state with Sx equals h bar over 2, this is the thing that I showed you way back at the beginning of the class. Okay, this is this thing right here. Okay, this is the state with Sx equals h bar over 2. Okay, so we want the inner product of this state with the state we calculated. Okay, so that means the inner product, so this state is, 1 over root 2, 1 over root 2. Okay, so we want the inner product is 1 over root 2, 1 over root 2 with the column vector a e to the minus I gamma b naught d over 2, b e to the I gamma b naught t over 2. Whoops, did I get the minus signs wrong? I think I got the minus signs wrong. This is a plus, this is a minus. Okay. All right, so this thing, magnitude squared. Okay. So that is, if I multiply out the row vector times the column vector, that's 1 over root 2 a e to the I gamma b naught t over 2 plus 1 over root 2 b e to the minus I gamma b naught t over 2. Magnitude squared. Okay, so let's see. If I factor out those root 2's, there's an overall factor of 1/2. Okay. And so then it is cosine alpha over 2, that's a, e to the I gamma b naught t over 2, plus sine alpha over 2, e to the negative I gamma b naught t. Magnitude squared. Okay, so let's finish this off. Okay, so this is 1/2. Well, so that absolute value is this thing times its complex conjugate. Right? So it's cosine alpha over 2 e to the minus I gamma t over 2 plus sine alpha over 2 e to the I gamma b naught t over 2 times cos alpha over 2 e to the I blah, blah, blah. I didn't do this in my notes. I'm just spontaneously doing it right now, so I sure hope this works. Otherwise, it will be really embarrassing. Okay, so here, this is 1/2. Let's see. So I need to multiply all this stuff out. Okay, so this is the first times the first. Okay, cosine squared alpha over 2. Okay, times 1. All right, and then plus cosine alpha over 2, sine alpha over 2, and then e to the minus I gamma b naught t. Okay. And then the second times the first. So it's again cosine times sine, and then it's all this stuff with e to the I gamma b naught t. And then the second times the second, so plus sine squared alpha over 2. Okay. And now what? This is 1/2. Let's see. The cosine squared plus the sine squared, that's equal to 1. Right? And then this stuff right here, this is 2 cosine gamma b naught t. Okay. And this is 1/2 cos alpha. So 1 plus cosine alpha cosine gamma b naught t. Well, okay, I hope I got this right. I think I got it right. It makes sense, I guess. This probability depends on the time at which you make the measurement, right? And so if you make the measurement at a certain time, I should add that to the question. Oops. At time t. Okay. If you make this measurement at time t, here is the probability that you would get a spin, and you measure the spin in the plus x direction. Here's the probability that you would get the spin in the plus x direction. So that is something else that you can do with the wave function, right? With the spinor answer. Okay. One more variation on this I can just mention in the last 4 or 5 minutes here. Up through here, in everything in this class, you know, I have assumed that nothing depends on position. Now, that's the simplest kind of experiment, but you know, what if the magnetic field does depend on position? That could happen too. So then there would be what people call an inhomogeneous magnetic field. Inhomogeneous means depends on position. That situation gets the name of the Stern-Gerlach experiment. Okay. And the interesting thing there is that the energy is the mu dot b, negative mu dot b, and b now depends on position. Okay, so that makes a force, which is the negative gradient of the energy. So that means that we're going to have different forces on different spin states. Okay, so let me just make a picture of that. All right, so if I want to make a picture, let's see, if this is X, no, if this is Y and X and Z, okay? So suppose you have a source of electrons and then there's some magnet here, which produces an inhomogeneous field, then that will make different forces on the electrons depending on their spin state. So the different spin states will go off in different ways. So you can have spin up that goes off this way and spin down that goes that way, right? So you can get then separate beams of particles. You could say, oh, well, I only want my spin up electrons, so I'll only look at this beam, or I only want spin down electrons, so I'll only look at this beam, okay? So if you only want one beam and not the other, well, then maybe in the lab, you could put a blocker somewhere, just block this one, and then you'll only see the spin up beam. Okay, and so the word for that is a spin polarized beam. So this is something that people do in real experiments as a way of generating spin polarized beams, right? So you can make a beam of electrons that all have spin up or all have spin down. And this is something which is analogous in some ways to an optical polarizer. An optical polarizer blocks off one polarization of light. You could say it blocks off light, if light is passing through this way, it could block off the horizontal polarization and only allow through the vertical polarization, right? And so that's what would be happening here. It blocks off the spin down and only allows through the spin up. So that's an experimental technique if people want to study one spin and not the other spin. All right. I am going to stop here, and yeah, I'll stop here. I'm running out of time. So let's continue on in the class tomorrow. Okay, so I'll see you at the same time tomorrow. Okay, thanks. Bye.